Well, hello there. This is my second lecture on miniature fuses. The first lecture included the following topics. It included the fuse types, the fuse thermal storage capacity, the I2t, few examples, standards for fuses, fuse breaking capacity, and temperature effect on fuses. Okay, my second lecture, this lecture, will concentrate on using the I2t expression to protect semiconductors. Okay, now we'll start with the I2t expression. The I2t expression, which stands for the fuse thermal storage capacity, and sometimes it's called the energy required to blow a fuse, or the fusing current, and in some literatures it's called the let-through energy, and its units is amp squared second. Okay, so let's get started. The I2t expression for a device is calculated using its ITSM, which is the maximum surge current, and the cycle time divided by 2. For a sine wave, the I2t would be equal to the I surge mode, ITSM, divided by the root square of 2, so that's the RMS of a sine wave, squared multiplied by T, where T for an SCR TRIAC or diode operated at 50 Hz is 10 milliseconds, and for a 60 Hz, that's in the States, it would be 8.33 milliseconds. So for this waveform, the one that you see in here, the ITS, the I surge mode in RMS, would be equal to the I surge mode divided by the root square of 2. So that's like just finding the RMS of a sine wave. Okay. And T, of course, equal to the cycle time divided by 2. Let's see this example, which was how manufacturer calculate that their I2t. That's example 3. From specifications of the BT137 TRIAC, the IT, that's the continuous current, okay, equals 8 amps. That's of course in RMS, and it's continuous. The surge mode, ITSM, equals 55 amps. And from the same literature, they are given the I2t to be 15 amps squared second. Okay, by calculation for a 50 Hz operation, we have that 55 amp surge current divided by the root square of 2 and squared, that's the RMS value, multiplied by the 10 millisecond, which is a half a cycle for a 50 Hz operation. That gives us 15.12 amps squared second. Very close to that given by the data sheet. Okay, another example here too. Example 4. For an MCR68, that's an SCR, I believe manufactured by Motorola. Given IT, the I continuous current is 12 amps, I surge mode 100 amps, and an I2t for that device 40 amps square second. By calculation, okay, and that's an American device, we have the I2t for it equal to the 100 amps over the root square of 2 n squared and multiplied by 8 milliseconds, should be around 8.33. It gives about 41.5 amps squared second, and that's close enough to the 40 given in the data sheet. Okay, even though manufacturers give their I2t based on a half sine wave, okay, which equals to 10 millisecond or 8.33 millisecond. That depends if you are operating in 50 Hertz or 60 Hertz. It still is possible sometimes to clear a fault in less that given time. Sometimes it's less than 10 or 8.3. You are able to clear that fault. So in a case like this, we are able to increase the surge current into the device, but at the same time, the I2t, the total I2t for the device will be decreased. Okay. So for an example, suppose we are able to clear that fault in 5 milliseconds instead than 10 milliseconds. Then that would be possible to increase that surge current. But the overall I2t will be less for the device. And that means it will have a smaller fuse to protect it. Let's see how that's done. When it's possible to clear a fault in less than T time, i.e. half a cycle, that T will be used as a half a cycle, which is used by manufacturers, then it's also possible to increase the value of the ITSM, the surge current, as given by the following equation. ITSM sub T, the smaller duration, would equal to the IT surge mode as a half cycle, the 10 millisecond or at 8.33, okay. And you divide that capital T divided by the small t, and all raised to the power of 1/3. That's from an RCA equation, a literature published by RCA. It's given the references at the end of the lecture. Okay. Then a new value of the I2t for the devices is, according to that, the I2t sub t for the small one, okay, because you are able to clear it in a smaller time. I2t sub t multiplied by small t over a capital T, the whole raised to the 1/2. Okay, that's of course the little one, let's say 5 milliseconds, divided by the standard 10 milliseconds for an example. That's a Motorola literature or Motorola book. For the RCA, it's the same thing. So the conclusion, even though you are able to increase the value of that surge current, the overall square T of the device will be less. Where the power of 1/2 or 1/3 has to do with the waveform shape under short circuit condition. For a sine wave, this value is 1/2, and for a triangle, it is 1/3. The value for t, that small t, must be practical and can be applied when that small t is greater than 0.5 millisecond and less than 20 milliseconds. So you can vary that duration to clear the fault. Okay, either increase it to about 20 milliseconds or decrease it to around 0.5 millisecond. And that will alter the value of the surge current and the value of the I2t for that given device. I think before we go any further, I would advise to go to an example just to capture the information that we mentioned, and we'll go back to this figure after we finish discussing our example, since we have the information fresh in our minds. Okay, let's see how that is done. Let's see that example 5 that we have in here. An SCR has the following specifications: an I surge mode of 100 amps and a T of 10 milliseconds. That's a standard duration. Then the fusing current I2t for it is equals 100 amps over 100 amps squared over 2, which is the same thing as 100 over root square of 2 are both squared. So this is the RMS value for it, multiplied by 10 millisecond, and that would give us a 50 amp squared second. That's the fusing for the device. Okay, now suppose we are able to clear that fault, or we would like to clear it in 5 milliseconds instead of 10 milliseconds. The value of the surge current would become 125 amps. Okay, and that's of course the fusing current for t equal 5 milliseconds. And the I2t for the whole device would become 40 amps squared second. So when you clear it at 10 milliseconds, it's 50 amps squared second. Because you stress that device more by increasing the surge current, it becomes only 40 amps squared second. And that means, of course, a smaller fuse to protect that device. Okay, and you can calculate the same value in another form, which is by using the new surge current value, which is the 125. We divide it by the root square of 2 and square it. That's the RMS value for the 125 amps peak. I will multiply that by 5 milliseconds. We get the same result, which is 40 amps squared second as the one above. Okay, that example hopefully clarified the idea and what happens when we try to clear a fault in a less than the standard time. Okay, now let's go back to the rest of the information concerning the I2t and the protection of the devices. Okay. Now the result. I2t value of a given device is based on a specific maximum on-state surge current for a given shape and time of a waveform. Usually half sine wave for a time of 10 millisecond or 8.33 millisecond, which equals T over 2 for 50 or 60 Hertz respectively. Accordingly, the I surge mode and the I square T value of a device can be decreased. That's when the new time is less than the standard time, or increased. That's when the new time is greater than the standard time, depending on the time and shape of waveform. Once the I surge mode max for a given application is known, as we are showing examples in here, I square T is calculated and the right fuse is selected. Here's a few examples. Suppose you are operating on 220 VAC, okay, and you have that surge mode up to 155 amps, and you created a short in here. Of course, you have that 155 because you divided the peak, which is about 310 volts, divided by the 2 ohms in here, okay, and neglecting the resistance of the wires, even though it should be considered. Or let's consider that the resistance of the wires is 2 ohm in this case. So you have 155 amp as a surge current, and it will be in the shape of a sine wave. In this case, for an example, suppose you have a cap that's going to discharge, okay, through the load, which was shorted, like the one before. So you have that resistance of the wire, or the resistance of the circuit. We have it's about 0.5 amp, and you have that cap was charged up to 50 volts. Okay, so they have that, you have that peak current through the device that needs to be protected, would be about 100 amps. Okay, and here the last one, suppose you have a load which is operated by a battery. In this case, it's 24 volts battery, and they have that resistance of the wire, which is considered, or resistance of the circuit, considered to be 0.5 ohms. So dividing that 24 volts by the 0.5 ohm, that equals about 40 amps of a straight line DC current. Okay, so these just a few of the shapes that you might encounter, and you know how to calculate the RMS for these things and find the I square T for the device under that condition, and hopefully find the appropriate fuse to protect it, which is usually, out of experience, should be about 50% of whatever you get out of calculation, to be in the safe side. Okay, another example that we saw before. We don't want to repeat it again. Okay, now let's see what we can get here. Okay. Another line here. That's pretty good enough. Covers the whole page. The I square T for different waveform shapes. Each waveform has a given I square T value. To know the exact value, complex equations have to be solved. To simplify the matter, find the IRMS for a specific waveform, square it, and multiply it by T, i.e. the I square T RMS multiplied by T, where the duration T must be practical, like we said before, should be greater than 0.5 millisecond but less than 20 millisecond. Okay, that's for a semiconductor protection. Example 6. In here we have 3 shapes. They're all triangle, as we see in here. But to be honest, I mean, each one of those, okay, will heat up the device in a different way, even though all of them have the same RMS value. This bit is confusing. I mean, even though they have the same RMS value, the device sees these 3 shapes differently. Okay. The RMS value for these triangles, IRMS equals I peak over the root square of 3, that's about 1.7. Then the I square T equals the I peak squared multiplied by T divided by 3. That's for the 3 shapes. Actually, waveform A stresses the semiconductor more than waveform B, while C makes the least stress. Okay. So when you start building up heat in the device, okay, let's say that warms up or heat up the device far more than applying the maximum peak, and then after that decrease it gradually. The waveform shape affects heat generation inside the semiconductor. That's the idea. Let's move on. Okay, we have that rectangular shape pulse, and we have that half sine wave, the standard one. Waveform D stresses the semiconductor more than E, because the RMS for it, of course, will be equals I peak squared multiplied by T, while the half sine wave will be equal I peak squared multiplied by T divided by 2, which means that D stresses the semiconductor twice as much as E. Okay. Measurement of the I surge mode for SCRs and TRIACs. For SCRs, the I surge mode and the I2t value are measured using half sine wave with 10 or 8.33 millisecond duration, 50 or 60 Hertz frequency. The ITS in RMS, that's the I surge mode in RMS, for a half sine wave, the one we see in here, it equals the I peak divided by 2. Of course, for a full wave, it would be equal I surge mode divided by the root square of 2. For TRIACs, the I surge mode rating is measured using a full wave, sine wave, with 20 or 16.6 millisecond duration. That's 15 or 60 Hertz frequency. While the fusing current, I2t, is calculated using the same SCR equation. So that's for a half. When you calculate the fusing current for both SCR and TRIAC, they will always use half a cycle, okay, which is the 10 or 8.33 millisecond duration. Okay, now in this case, just give an idea. For an SCRs, the I surge mode would be equal 2 times the okay, that's the RMS for it. Oh, yes, okay. Because the peak current divided by 2 for a half sine wave, it's equal to its value in RMS. And that one's divided by the root square of 2. Yeah. Now example 8. For the BT139 TRIAC, given the I surge mode equals 115 amps, the IT in RMS, the continuous current 16 amps, and the ITS in RMS equals 81 amps. Of course, this figure is taken from that one. This value is taken from the surge mode. and I square T equals 65 amps square second. That's all taken from the data sheets. Okay. The I square T would equal to I surge mode squared and divided by 2 multiplied by T, and that equals to 66 amp squared second, very close to the 65. And the ITS, which is an RMS value for that surge current, which is 115 divided by root square, which equals to 81 amps. That's the same value given in the literature. This is how they write their numbers in their literature, how they calculated. Okay. And here, for triacs, Motorola provides the rating curve relating the I surge mode to the number of cycles. Okay, that's in figure 13. We can see here the first cycle, the second cycle, the third cycle, okay, and so on and so forth. While Philips provides a similar curve relating the ITS, which is an RMS, okay, that's the RMS of the peak surge current, to the duration. This I believe this gives more information on what happens between the 1 millisecond up even to 10 seconds. Imagine that, 1 millisecond to 10 seconds. That's a lot of duration, and you can get a lot of information out of this figure. Okay, and you can see the same information that were presented in example 8 up there, okay, with the graph that we have in here. So that's the RMS current at 80 amps that was calculated, okay. And another piece of information too, and this is what they call it when you try to decrease the duration and you are able to clear a fault in less than the standard time. For example, if it's 5 milliseconds in here, you are able to raise that surge current from 115 up there to 162 amps. Okay, and that's how you get your RMS out of it. You divide it by 2, you get that RMS out of it. Okay, and that's value which is 115 in RMS. You can see it right here in the figure, and you get that standard 80 amps over here. And these are the duration. These are the half cycle between there to here, where you have a fixed that current. That's the duration. It's the 10 milliseconds. Okay, and after that, let's see some of the references that were there from RCA and from RS Data Library, from a book in Power Electronics. And let me conclude by the crediting laboratories. Usually, their symbol is engraved or written in any given fuse. So you have as many as about 2, 4, 6, 8, 10, about 20 labs. And the kind of symbol that they use. Of course, this is the American one under Lateral Laboratory, and you have the Canadian one. Like we said before in our first lecture, those two labs, they test fuses differently. Therefore, the value of their fuses are not interchangeable with the rest. They're an international type. Okay. I hope that was useful, and I would like to thank you for watching, and see you in my next video. Bye for now.